Hello everyone, welcome back to the discussion on sensors commonly used in mobile robots. In the last few classes, we discussed about the basic principle, operation principle of some of the sensors. So before closing the discussion on sensors, let me briefly talk about another class of sensors which are very commonly used, though they are not very much needed in localization and other aspects, but they are used for many other applications in mobile robots. So they are basically the proximity sensors. Proximity sensors do non-contact sensing compared to the sensors like limit switches, which actually depend on contacts to sense objects. Proximity sensors do a non-contact sensing. So the presence or absence of an object or movement of an object proximal to the sensor can be detected by this kind of sensors. As you can see here, there are different kinds of proximity sensors. One is basically the inductive type, which uses the eddy currents that are generated in metallic sensing objects by electromagnetic induction. So that is one basic principle where they go for the inductive principle. When the metallic objects are close to the sensor, because of electromagnetic induction, there will be an eddy current formation, and that will result into some kind of changes in the sensor, and that can be used as a detection of some objects proximal to the sensor. So that is basically the inductive type sensor. The other one is capacitive type. Basically, again, this also will be having a non-contact type. So the detect changes in capacitance. So here the variation in capacitance is measured when the sensor is close to an object. And there are other types also, like optical and ultrasonic sensors. Optical sensor, as you know, when it is reflecting a light, or the light is getting objected or obstructed by some objects in the vicinity, that actually can be given as a sensing of the presence of object near to the sensor. That is the optical. Similarly, ultrasonic also. Ultrasonics will be emitting ultrasonic waves, and then that will be reflecting from a object, and then that can be used as a measure of, or as a sensing of objects near to the sensor. So any one of these principle can be used, whether it is inductive, capacitive, or optical or ultrasonic can be used to detect objects proximal to the sensor. So when you attach this sensor to the robot and the robot is moving, it will be able to tell you whether there is an object near to the robot or not. It won't really tell you the distance to the object or the type of object, etc. It's purely tell you whether it is the object is close to the robot or not. That is basically the proximity sensor. Let us look at the working principle of these sensors. So the inductive type. So this is the basic construction of an inductive type sensor. So there will be a coil which will be actually actuated through electrical supply, and there will be an oscillator which will generate high frequency electromagnetic field. And when a metallic object comes close to that, will get an eddy current on the surface. And as the sensor is closer to this, the eddy current increases, and that will actually lead to some changes in the oscillator, and then the oscillator will not be able to provide the necessary oscillation as the current increases, and that can be used as a measure of object close to the sensor. That is basically the principle of inductive type sensor. Okay, so it is very accurate compared to other technologies, because the variation in the oscillator circuit only need to measure, and once we can measure that, it will actually tell you whether there is a change in the oscillation, and that will tell you whether there is a presence or absence of object. And have a high switching rate, so it can actually do very fast response, and very harsh environment also this can work. But the disadvantage is that it can only for metallic targets. So currently they are actually used for metallic. There are non-metallic sensors also, but most of the inductive one which actually follow the metallic target only. and very limited range. If the object is far away, then you won't be able to create the necessary D current, and therefore you won't be able to get the sensing. So, lot of few disadvantages are there for the inductive type sensor. As you can see, there are a lot of commercially available inductive type sensors in the market, and they are not very costly. You can actually get it at a low cost, these kind of sensors, and the output is only a presence or absence of an object. That's all it will tell you. Coming to the capacitive type, as I mentioned, the variation capacitance is basically measured in this case. Okay, so they can be used for non-metal objects because it's not on inductive principle. So you can actually use for non-metal also. You can use this capacitive principle, and they produce electrostatic field instead of an electromagnetic field. So electromagnetic field, instead of electromagnetic field, you can go for electrostatic field. And then, as you can see here, the sensing object, and this is the sensor. So you will be able to see the variation in the signal when there is a presence of an object. So this variation can actually be observed in the sensor, and that can be interpreted as the presence or absence of an object. So that is the principle of capacitive type sensor. Again, you can see there are very commercially available sensors are there, can be easily attached to a robot, and then can be used for checking the proximity of a robot close to any object. So it can detect both metallic and non-metallic objects, and high speed, good stability, good in terms of power usage, and low cost are the benefits. So it may get affected because of the temperature and humidity, and very not accurate compared to inductive sensors, and difficulties in design. So accuracy wise, the capacity may not be so good and may be a bit difficult to design, but otherwise they are very good, and high speed and stability is there for sensing using the capacitive type sensors. And others are there actually like ultrasonic. So I am not going to the details of all these sensors. So ultrasonic basically provide you, it will produce a ultrasonic wave, and then there will be a receiver which will actually receive the reflected signal, and whenever there is a reflection coming to the sensor, that will that can be interpreted as the presence of an object near to the sensor. That is basically the ultrasonic. And similarly, you have the optical proximity sensor, optical proximity also with the reflection of light, or there is a receiver at the other end that also can be used for checking whether there is any object in the near to the sensor. So we can go for inductive, capacitive, ultrasonic, or optical proximity sensors in robotics. As I mentioned, they just provide you the information whether the robot is close to an object or not. No further quantitative information will not be available from this kind of sensors, but still they have wide application, because in many cases you just want to avoid some obstacles, or just want to check whether it has reached a particular end of path or something like that. So in that situations, this kind of sensors are quite good, and they are cheap and then easy to integrate, and therefore they have a lot of applications in mobile robotics. So that's about the different types of sensors we use in robots. But before closing the discussion on sensors, I just want to highlight one important point which I already mentioned a few times about the sensor error and the error propagation. So as I mentioned, the sensor errors are, there can be errors which can be compensated using calibration, and there are random errors which cannot be really modeled or predicted. So we need to have some understanding of what is the error in the sensor, and how this sensor error will lead to additional errors in the estimation of sensor characteristics, the robot pose or other characteristics of the robot. So this is why we need to know what is the error propagation model that is normally used in robots. So as I mentioned, the sensor measurements are corrupted by measurement noise, which fluctuates randomly, and we have to represent them using random variable, and statistical properties are characterized by PDF, that is the probability density function. And normally we go for the Gaussian PDF, where I mentioned that it can be presented as a Gaussian distribution with a mean value and a standard deviation. But there are sensors which represent non-Gaussian behaviors also, but in general most of the sensors can actually be classified under this category, and then we can use it for predicting the errors in the estimated cost of the robot when there are errors in the sensors. So, to explain this, please have a look at this diagram. It shows the x versus y plots. Now, assume that okay, to take an example of a mobile robot, and we have two wheels. The robot is moving, and then we say that this is having a speed of omega 1, this is having a speed of omega 2. Now, we use this we use two sensors to get the values of omega 1 and omega 2, or we use a sensor to get the speed of the wheel or the angular position of the wheel based on the sensor reading. So, we take this, and then we want to know how much the robot has traveled in this direction, in its x direction. So, we want to get the x position of the robot, and we know that if we know the radius of the wheel and the RPM of the wheel, and once we have these parameters and then some other robot parameters if you can have, then we will be able to get the x and y as a function of this omega. So, we will just say it is a function of omega. Of course, it may be function of many other parameters, but for the time being let us assume that it is a function of this speed. Now, I have a sensor which actually measures this omega, and then I use that one to estimate the position of x. Now, the question is, if I have an error in omega measurement, if there is an error in omega measurement, what will be the error in x, estimated position x? So, this I need to estimate, because I know only about the sensor and the sensor characteristics, and based on that I need to find out what will be the approximate error in the position x if I calculate the position x using the value of omega. So, this is basically what we need to know, or this is known as the propagation of error from the sensor to the estimated position x. So, we have a propagation of error from the sensor reading to the estimated position of the robot x. So, now if I represent this as a function of x, so in this case if I write this as y is equal to f of x, that is I am estimating y as a function of x, and then I have an error in x. So, that is what actually plotted here. So, if I am measuring this x, and the error in x can be shown as a distribution like this with the mean value mu x, and then a sigma, which is the standard deviation. If this I know, if I know the sensor mean value and its standard deviation, can I find out what will be the error in y, mu y, and the sigma y? So, if I can estimate the mu y and sigma y, then I know what is the error in y because of the error in x. So, this is known as the error propagation model, and we need to have a relationship between the mu y and mu x, or we need to know what is mu y, or how can I estimate mu y or sigma y. The sigma y is important because that actually shows the how much error will be there, variation in the error. So, if I can estimate the sigma y, if I know these parameters, then we call that as an error propagation model, and this is basically the error propagation law, which states that we can find out the error in the estimated value if we know the error in the sensor or the measurement. So, that is basically the error propagation law, and what it states. So, we will take a one dimensional case that Cy, which is the covariance in y, covariance when it is a multi-dimensional one, you will have a covariance. So, Cy. So, Cy can actually be given as C fx Cx fx transpose, where Cx is the error covariance in x. If the error covariance in x or the mu x or the Cx is known, then we can actually get Cy as Fx Cx Fx transpose, where Fx is known as the Jacobian, which depends on the function y of f of x. So we can write it as the Cx is the covariance matrix and Fx is the Jacobian, which is defined as the transpose of the gradient of Fx and is given as, so if y is equal to f of x, so if you have y is equal to f of x, then the Jacobian Fx can be given as f1 by partial derivative of f with respect to x1, x2, etc. So if it's a multidimensional one, then we will be able to get these elements as partial derivative of f with respect to x. So if you have multiple variables x1, x2, etc., then you will be able to get this as a like this. So this is the Jacobian which can be used for calculating this. So Fx, Cx, Fx transpose will be the covariance in y when there is a covariance x in the measured data. So this error propagation law is widely used in estimating the position of the robot when we are using sensors to get the parameters. So when a sensor is used to get the distance to an object, and then using that distance you are estimating the position of the robot, we need to know how much error will be there in the position when we have some error in the estimated or the sensed distance. So that is basically the requirement in localization of robots. So we will be using this error propagation law in order to get the estimated position of the robot, and as the robot moves, this covariance keeps increasing, and therefore you will be having a lot of uncertainty in the estimated position of the robot with this kind of measurements. We will see this how to use this one in the localization as when we discuss about localization of mobile robots. So that's about single sensor issues. When you have a sensor and you use that sensor for estimating position or the velocity or some other parameter of the robot, you will be getting errors. So how do we actually avoid that kind of errors? So one way is to go for multi-sensor data fusion. So you don't depend on a single sensor, you use multiple sensors and then fuse this data and then have a better estimate of the position of the robot. Though there is error propagation, still you will be able to correct the errors or to bring down the errors to some extent by having a multi-sensor data fusion. This is the process of combining observations from a number of different sensors to provide robust and complete description of an environment or process of interest. So you will be able to combine data from different sensors and then use it for describing the or use it for getting the estimated position with much more accuracy. It actually has got wide application in many areas of robotics, object recognition, environment mapping, and localization. So how is it done? So you take the sensor data, sensor 1, sensor 2, etc., and then there will be some kind of filter algorithms. So we use some filter algorithms to fuse this data and then reduce the error. So as the robot moves, that error keeps increasing. So to avoid that, we use multiple sensors and then fuse this information using some filters, and we'll estimate the position of the robot. That is the way how we keep on doing the estimation of the position and the attitude of a mobile robot using sensor fusion. And we have many filters like navigation filter to get the navigation related data, and these filters will be having different features. So you can actually go for complementary filters or fixed gain observer or Kalman filter or particle filter. So there are many such algorithms available, and some of these we will be discussing later as when we talk about robot localization, mobile robot localization. We will be talking about some of these filters, not all the filters, but at least I will be discussing 1 or 2 filters and see how these filters can be used to fuse the information from sensors and then estimate the position of the robot in a much better way by reducing the error propagation or reducing the error in the estimated position and attitude of the robot. So that's going to be the that will be discussed in the next few classes. Okay, so let me conclude the discussion on sensors with that. So we talked about the importance of sensing and the perception in mobile robots. What is the reason why we need to learn about these sensors? The sensing and perception is an important aspect of mobile robots. And then we talked about the characteristics of sensors, like the repeatability, resolution, bandwidth, etc. And then we talked about different types of sensors. We talked about position sensing, encoders. We talked about velocity sensing, and we talked about accelerometers, IMUs, etc., etc. And briefly talked about vision-based sensors or the image-based sensors, where we can do image processing, collect the image using camera, process the image, and then use it for some information, to collect some information, and that information can be used in mobile robots. And finally, we talked about fusion also, how to fuse different data. Of course, we did not go into the details, but just mentioned the importance of sensor data fusion and how that can be used for improving the position or the estimated position and attitude of mobile robots. Okay, so with this, I'll conclude the discussion on sensors. From next lecture onwards, we'll talk about mobile robot localization, especially for autonomous robots. How do we do the localization, and then how can we use the sensor fusion to improve the accuracy of localization. Similarly, how to use the localization and mapping in order to create a map for robots. So that will be the discussion in the next few classes. And we need to discuss a little bit about the kinematics also, and how can we use the kinematics to, of course, you already have some information about the kinematics, so I'll not be going to the details of kinematics, but I hope that you will be having the basic knowledge of kinematics to when we use this information for localization. Okay, thank you.